All right, example 7. Find absolute maximum and absolute minimum values of f of x equals 2x cubed minus 12x plus 2 on the interval negative 2, 3. We have a two-step process here. Number 1, find all your critical numbers. Three-step criteria for critical numbers that we learned yesterday is derivative equals 0, derivative is undefined, endpoints of an interval. As we can see, the interval negative 2 comma 3 tells me that x equals negative 2 and positive 3 are critical numbers. Even if there was a parentheses on that interval, we still want to include them as critical numbers. Just know if a point occurs, such as let's say it's 3 parentheses, and let's say 3 comma whatever is supposed to be an absolute maximum minimum, the point doesn't exist, so you have to throw it out. Okay, so that is a possibility. More often than not, the interval is going to be bracketed though, so typically we're going to see closed circles. But again, if they did put a parentheses, it's still a critical number. It's just the answer for that specific number doesn't count. All right. The second thing we do for criteria 1 and 2, we need a derivative. So I take this function f prime of x, and I make the first derivative, which is going to be 6x squared minus 12. And I have to solve that equal to 0 for criteria 1. And this is easy enough just to solve by hand. I get 6x squared equals 12, so x squared equals 2. So x is going to equal plus or minus the square root of 2. Go a couple decimal places for that. If you know what the square root of 2 is off the top of your head, great. Otherwise, calculator knows it. Square root 2 equals 1.414. We go a couple decimal places, 1.41. Only numbers within this interval matter. You can see both of these numbers do fit within negative 2 to 3, so they both count. But let's say this said negative 1 to 3, the negative 1.41 could be thrown out at that point because it's not on the interval. So just because you get a first derivative equal to 0, if the interval doesn't include that number, it doesn't count. So x equals 1.41 and negative 1.41. And finally, if the derivative itself is undefined, we can see the derivative itself is a polynomial structure. Polynomials are never undefined, so there is no critical number based on that. So that's priority 1. If you're asked to find the absolute maximum and minimum value on an interval, find all the critical numbers. So at this point, of all the numbers in all the world, those 4 matter now. Everything else doesn't matter. What I want to do then is I want to evaluate the function f, this function, at each of these 4 numbers. F of 1.41 equals something, f of negative 1.41 equals something, f of negative 2 equals something, and f of 3 is equal to something. And I'm evaluating the same function for multiple numbers. The easiest way to do that is to go over here to my y equals, enter the function I want to evaluate, 2x to the third minus 12x plus 2. And go to my table and enter the 4 numbers that I care about, 1.41, negative 1.41, negative 2, and positive 3. And my results are negative 9.31, positive 13.31, positive 10, and positive 20. All right. So at this point, I've just evaluated the function at each of my critical numbers, and the absolute maximum is the biggest one that shows up. This number is the biggest. So of all these 4 numbers, that's the biggest number. That's the absolute maximum. The absolute minimum is the smallest one. This one looks like the smallest one to me. Negative, everything else is positive, right? So I'm going to write absolute maximum. Feel free to go ABS-MAX, absolute maximum, of 20 at x equals 3. Absolute minimum of negative 9.31 at x equals 1.41. Okay. Now, the usefulness of having an absolute maximum and minimum is this. If I wanted to graph this now on this interval, and I went window, and I went x equals negative 2, 3, right? That's my x interval, right? I've got a maximum value of 20, a minimum value of negative 9.31. So if I went y minimum, let's go negative 10, that's smaller than the smallest number, right? And let's go 21, that's bigger than the biggest number. I know the graph's going to fit on that. Let's go to 5 scale there, graph. there goes the graph, and it stayed on the screen, and then it stays on the screen. Perfect. All right. And that just verifies what we can already see. That's a local minimum, that's a local maximum, that's an absolute minimum, absolute maximum. And again, that just verifies what we already saw. But again, this helps us if we were graphing. We've now got 4 coordinates. The 4 coordinates we got, let me bring this over here. And graphing is not a requirement, but I just want to show you what this did for us. I got this point, and I got this point, and I got this point, and I got that point. Suppose I got nothing else but those 4 points. That'd be a better way to do this. Get all that stuff out of the way. Go away. All right. I had nothing but those 4 points. I know that's the highest point, that's the lowest point in this area. I can make the graph pretty well from that. Just knowing those 4 points and having the specific criteria about them. Again, that's where we're going with this. This is just one technique that's going to help us find a good graph. And again, just with 4 simple points, we get a pretty decent sketch. There's a few more points you can find within these things that give you a little more detail, that give you a little bit better idea of what the graph looks like. And each time you get a little bit more detail, you get a much more accurate graph with, again, very few points to do it.